Hi class, welcome to our first attempt at tackling infinity. What is it? Simply, it's really large numbers. Now, if x is approaching this guy, infinity, you move really far to the right. This is barely 4 million. That's nothing. Infinity will take you way further than that. Or really far left if x is approaching negative infinity. Then you'd go all the way down to the negative millions, billions, and trillions. If y is approaching this guy, infinity, you move really far up, all the way up to millions and billions and trillions on the y-axis. Or really far down, if approaching negative infinity, then you'd go that way. Really far right or really far up? These extremes, what could it mean? It could only mean one thing, guys. And you guessed it, asymptotes. Dun, dun, dun. So as x moves really far to the right, we're dealing with the horizontal asymptote. X approaching infinity, horizontal asymptote. Or if the y values are approaching infinity and you're going really far up, that would only mean a vertical asymptote. So y approaching infinity is going to get you a vertical asymptote. Class, you guys did a calculator lab. That was studying the effects of having x approach positive or negative infinity. So I want you to think about what you've noticed so far. And hopefully you've come to some sort of an idea or recognized a pattern that the result or the limit as x approaches infinity of a function or as x approaches negative infinity of a function, whatever these values equal happen to be, if they exist, let me write that instead of equals. If they exist, if these limits exist, then they're equal to the horizontal asymptotes of the function. That was the conclusion that you were supposed to make having completed that calculator lab successfully. So basically, when you're asked to find a limit as x approaches infinity or a limit as x approaches negative infinity, and remember, this one is far right, this one is far left. Really what you're being asked to find is a horizontal asymptote. So what we need to review are how to find horizontal asymptotes, because that's basically what you're going to be doing. Now there's a limit theorem in your book that I wanted to point out here. And the first one states that the limit as x approaches infinity of 1 divided by x to some power, where n is a positive integer or positive power. So what's happening here is you have the number 1 being divided by a value of x that is approaching infinity, that is heading way off into the millions, billions, and trillions. So you're taking a really tiny number and dividing it by a gigantic number. So let's see what that would be like. Tiny number divided by a gigantic number. In this case, I'll use the tiny number 1, and I'm going to divide that by a gigantic number, like 1 million. I would get 0.00001 if I divided that tiny number by that gigantic number. And I don't know about you, but this to me is practically getting really close to 0. It's almost nothing. It's like microscopic. So the limit as x approaches positive infinity of 1 over x to that power is equal to 0. That's the theorem in your book. I would like to extend that a little further. And I would like to say that if you take a limit as x goes to infinity of any constant, not just one, any constant divided by x to the n, that limit is going to go off to 0 as well. Let me move this writing out of the way here. That limit is going to equal 0 as well, even if that constant was large. So let me put c equal to any constant. Even if that constant was large, remember, x is approaching infinity, and I'm raising it to a power. Let me make that more obvious too. So even if c was a billion, well, then I'll just make x a trillion or a zillion. I mean, x is growing infinitely large. There's no knowing when x will stop, okay? So even if c was gigantic, x can always be giganticer or more gigantic. And so at any rate, this can grow so big that this will end up being a tiny number no matter what, divided by a gigantic number is going to equal something really small. Okay, and then likewise, the limit as x approaches negative infinity of 1 over x to the n would also be 0 because I'd be getting a really, really small negative number. And then the extension applies to that as well. Okay, so that's the theorems in the book. I would like to even venture further. So if you could just use this piece of scratch paper or just turn this paper over and we can go on the back. When you're trying to find limits as x approach infinity or negative infinity, as we mentioned, you're trying to find a horizontal asymptote. Now, what we have to understand about horizontal asymptotes is these are the values that y is approaching as x gets crazy large. Crazy large. We're talking billions, trillions, zillions. So if you have something like, let's look back here, something like example 1, this y value, this right here is the y value, or the f of x. We're trying to figure out what this whole entire quotient is approaching as x gets crazy large, as x approaches infinity, moves really far to the right. Well, for large values of x, we have to ask ourselves something. Does the minus 13 really have that big of an effect for large values of x? Does this plus 5 really have that big of an effect on large values of x? I mean, let's think about it. Let's say x was 1,000,000. I'd be plugging 1,000,000 into that expression. So then I'd have 6,000,000. Take away 13. Okay, let's imagine this. Let's imagine you have $6 million in your bank account. And you have to pay $13 for some fee. I mean, it's chump change. It's like a drop in the bucket. It's like you wouldn't even notice it was missing because 13 is so tiny compared to 6 million. But that's not all. X is going to keep getting larger. You might even be dealing with 6 billion. Take away 13. Remember, X can keep growing. X is growing and growing. It's going to get even larger than that. Eventually, that negative 13, I mean, you don't even notice it. You don't even notice it. So, for large values of X, we ignore those numbers that aren't going to have any effect. And we only look at the highest power of X in both the numerator and denominator because those are the only things that are going to have any impact on the value at all. Because this 6x is going to grow with x, and this 2x is going to grow with x. But the 13 and the 5 are just going to stay the same size, and right now they might seem big, but compared to 6 billion or 6 trillion or 6 zillion, they're nothing. So, what we do in finding a horizontal asymptote is we only look at the higher powers of x or the more dominant because sometimes we won't be looking at powers of x. So we look at the more dominant part. You switch to pen. More dominant parts of the numerator and denominator. Okay, we only look at the higher powers of x, i.e. the more dominant parts of the numerator and denominator. And we just focus on those. So we only look at those. Okay. So then second, you simplify. Okay, so let's go back to this example 1. So if I'm only focusing on the larger parts of the numerator and denominator, I'm really only looking at the 6x and the 2x. So I'm really looking at this limit. Okay, again, x is approaching infinity. So imagine you're plugging in 1,000,000 into both of those x's. Then this would turn into 6 million, and this would turn into 2 million. If you divided those, you'd have 3. Okay? So it's like basically what's happening is these x's are growing at the same rate because they have the same power. If I plug 1,000,000 in there, I'm going to get just 1,000,000 times 6 and just 1,000,000 times 2. And no matter what, if I plugged a billion, same thing, a trillion, same thing, it's like they're growing at the same rate, so they cancel each other out. And I'm just left with 6 divided by 2. So that limit as x approaches infinity of this whole quantity, it just turns out to be 3. So let's summarize that on the back. If the powers of x are the same in both the numerator and denominator, then the limit as x approaches infinity of that function is going to equal, you just basically divide, equals, but you divide. It equals what you get when you divide the coefficients of those higher powers, of those dominant x terms. So it equals what you get when you divide. The coefficients of those dominant x terms. So in this case, x was growing at the same rate. It was a power of 1 in the numerator, a power of 1 in the denominator. I ignore the 13 and the 5 because they have no effect for large x values. And then because these x's are growing at the same rate, they cancel each other out, and I simply divide the coefficients of those dominant x terms, and I get 3. That 3 is equal to the limit as x approaches infinity of this whole thing. It's also equal to the horizontal asymptote of the function. They're one and the same. Okay, so this example was if the powers are the same. Second example. Again, we follow step 1. Step 1 is you only compare highest powers in numerator and denominator. I'll just call that top and bottom just to save myself some time. Compare the highest powers in top and bottom. So I have a power of 1 in the numerator and then a power of 3 in the denominator. Remember, I ignore 10 and the 5. I ignore them because for large values of x, and this now, okay, it's negative infinity, but that's still a large value. It's just a large negative value. But we're still talking about 1,000,000, a trillion, a zillion, all that stuff. Okay. These are large negative values. For those large negative values, this negative 10 and this plus 5 are not going to make a big impact. They're not going to have a huge difference. So we ignore them and we only look at these powers. Okay, so then what I'm really looking at is the limit as x approaches negative infinity of 3x over 4x to the third. Okay, step 2, simplify. So if I simplified this further, I would end up with 3 over 4x squared. There were more x's in the denominator than there were in the numerator. That means this is more dominant. When I go to plug in a large number, say 1,000,000, if I plugged 1,000,000 in for x, I'd have 3 times 1,000,000, and then I'd have 4 times 1,000,000 cubed. I mean, holy mother, that would be a gigantic number. Definitely larger than 1,000,000. In fact, when I cancel that, I'd end up with 1,000,000 squared. So you can see this denominator is going to way overpower the numerator. I'm going to have a teeny number 3 divided by a gigantic number. And if you remember our theorem up here, if you have a teeny number divided by a gigantic number, as that x is going off toward negative infinity, which I wrote wrong here, I'll fix that right now, then the overall y value, that quotient, tiny divided by gigantic, is going to go towards 0. It's going to get really, really tiny and approach 0. So this limit here is going to equal 0 based on that theorem from before. So what we can conclude is that if the power in the denominator is larger, the limit every time is going to approach 0. And this is true for positive and negative infinity. I'll just write negative for this example since that's how it was. And that's true for any time that your denominator has a greater power or more dominant than your numerator. Third scenario is I compare my greater powers. Now that negative is important here because that means I'm going to have a negative number up here. I compare my higher powers and I ignore the 1 and the 7. Okay? And I'm looking at the limit as x approaches infinity of negative x squared over 10x. I'm going to simplify that a little bit. Okay. Now I'm faced with a little bit of a different situation where now my numerator is more dominant than my denominator. I'm going to have a gigantic number divided by a tiny number. Okay, so let's just plug in a value. Plugging in values is a great way to just investigate what the heck's going on. I'm going to do that over here as like side thinking. Let's say I were to plug in 1,000,000 in there for x, because remember it's approaching infinity, so 1,000,000 is one of the values it's going to hit. It'll get bigger than that, but that's just one that we can check. So I'd have negative 1,000,000 divided by 10. Okay, so that's still negative 10,000. Yeah, it got a little bit smaller, but still gigantic. And remember, that million can be a billion, a zillion, a trillion. It just keeps getting bigger and bigger. So even though you're dividing by 10, it's this overall quotient, the overall value is still growing really large as x approaches infinity. So this has no limit. There's no limit to what it can be. It's just going to keep, this whole quotient is going to keep getting larger and larger, and it's going to be a larger and larger negative because I have this negative value being divided by a positive. So this limit, we're going to say, approaches negative infinity. Meaning it really has no limit. It just has no value that it's going to approach. It's going to just get really, really, really negative indefinitely. So because of that, this does not have a horizontal asymptote. No horizontal asymptote. So, what did we observe here? We observed here that when the power in the numerator is greater than the power in the denominator, there will be no horizontal asymptote. No horizontal asymptote. So, if you can follow me here. So, the limit then, as x approaches infinity or positive infinity or negative infinity, will either equal positive infinity or negative infinity. Oops, not negative 8, just kidding. Okay. So that's what happens when the power in the numerator is greater than power in the denominator. There is no horizontal asymptote, meaning the limit is not going to be a number. It's going to just either go off to positive infinity or negative infinity. Okay. Last example of this session, or this part of it, is comparing something inside a square root. Now remember, we're looking at dominant parts only. So I'm going to ignore that 3, and I'm going to ignore the 1 because they're not going to have an effect when x is really large. Also, I'm going to keep in mind, so side thinking bubble here, the square root of x squared, no matter what, is going to stay positive. Even though this is approaching negative numbers, when you plug those negatives into the denominator, because of the fact you're squaring them and then square rooting them, those values are going to remain positive. Meanwhile, in the numerator, those values are definitely going to be negative because I'm plugging in negatives in for x. So 2 times a negative number is going to be a large negative number. Okay, so just keep that in mind. So I'm going to just look at the 2x. I'm going to just look at the square root of x squared. I'm going to simplify a little bit. Now remember, the square root of x squared is technically equal to the absolute value of x. Okay? So these x's, remember, when you have x over absolute value of x, that either equals 1 or negative 1, depending on if x is positive or negative. This x is going to be negative. So I'm going to plug a negative number in here, like negative a million, and then another negative number in there, same negative. So here's another thinking bubble. So let's say I plugged in negative a million. I'd have 2 times negative a million divided by the absolute value of negative a million. Well, this would turn positive. These would cancel, leaving me with a negative, and then times 2. So this limit is going to end up equaling negative 2 because it turned out that the powers were the same, because the square root of x squared is really just x to the first. So I ended up with x to the first divided by x to the first. I just had to be careful about the signs. The numerator was negative, the denominator was positive, so those canceled out because they had the same power, but left a negative over. There was a negative 1 left over that had to multiply to the 2, and so I got negative 2 there. I'd like you to try a few examples that I'll write out for you here. Try these problems, see what you get, and then join me for the next video. I'll see you there. Welcome back to part 2. So as you can see, I have the solutions to the U-tries. So these are limits as x is approaching infinity. But there is such a thing as a limit of y, I guess, as x is approaching a finite number. So this c is just representing a constant, a finite number. And so what can happen is x could be approaching that finite number c, but the y values, as x is approaching a number, the y values might be heading off toward infinity. And that means that, so this means that the y values are going up, basically, without stopping. As the x is approaching some number. And then if it's going toward negative infinity, oh, and I should also say that this can only happen if it's on the right or left side. I can't approach infinity from both sides. It would have to only be from either the right or the left. So this would mean that the y values are going down without stopping. There's no limit to how low they can go. As x is approaching some number either from the right or from the left. So what that looks like is a vertical asymptote. So let's say we have like some function, and let's just say x equals c is right there. And you've probably seen these types of functions. They're usually rational functions like these examples here, because we end up dividing by some number that gives us 0, or that gives us a 0 in the denominator, which is bad. And so we see stuff that goes like this, or like that. And so this top one here, this would be where f of x would be approaching infinity. Is this right here. So this would look something like the limit as x approaches c, I'll just call it c, from the right, because on the right-hand side, the y values are going up. So that would equal positive infinity. Meanwhile, this one over here is on the left of c, just as an example. So you would say the limit as x approaches c from the left, well, there is no limit. It's going down without bound. And since it's going down, we'd say that limit equals negative infinity. So that's what these graphs look like. And remember, what creates them is a 0 in the denominator. So maybe you could write that here as well. These are created by zeros in the denominator. That's what would create a vertical asymptote, and that's where a function would start heading off toward infinity. So there are some theorems in your book that go along with this. And there, I'll give you the book ones, and then I'll give you my extension. So these are the ones from the book. And they state that if x is approaching 0 from the right of some fraction where you have 1 divided by x to some power, and I'll just put n as a positive power, then this limit would be heading off toward positive infinity. So then the question is why? Okay, because now I'm dividing a number by a really, really, really tiny number, because this is approaching 0. So now I would have 1, which seems small. But the closer I get to 0, and so let's plug in like 0.0001. The closer I get to 0, these numbers get so tiny, okay, that this actually equals, this is really the same thing as 1 divided by 1 over 10,000 actually. 4 zeros. That's what this is. So it's like 1 divided by 1 over 10,000. Well, that's just the reciprocal. So 1 divided by 0.0001 turns into a gigantic number. So when you take a constant and you divide it by something that's getting increasingly smaller, what you're really doing is taking the reciprocal of that increasingly smaller number, which gives you a gigantic number. And since this number is getting smaller and smaller and smaller, it's approaching 0, this number is getting larger and larger and larger and approaching infinity. And the same thing happens if I were to approach 0 from the left. I would have, okay, but this one you have to be careful. I would have positive infinity if n is an even number, because then these would become positive numbers, because a negative number raised to a positive is a positive, or negative infinity if n were an odd power. Because if I had an odd power there, I'd have a negative number risen to an odd power, which would stay negative. Okay, then for my extensions. So I'm going to say this. So first of all, let's say if the limit as x approaches a of f of x equals c, and c is greater than 0, and the limit as x approaches a of g of x is 0, then the limit as x approaches a of f of x divided by g of x is either going to be positive infinity, have this be from the right. Then it will be approaching positive infinity if g of x is positive, or if g of x is approaching 0 from the positive side, and then negative infinity if g of x is approaching 0 from the negative side. because this is actually approaching a number. The limit as x approaches a of f of x is some number. It's a constant. It would turn into a constant. Dividing by something that's getting really, really small. So g of x is approaching 0. It's getting really, really, really tiny. So as we looked at earlier, if you take a constant number and divide it by a really, really teeny number, you're going to get a really large number. The positive and the negative just depend on whether or not you get a positive if you divide it or a negative if you divide it. And then the same can be true if I said the limit as x approaches a from the left. The same would be true. It'll either equal positive infinity or negative infinity if the top is turning into a constant like 5 or 10 and the bottom is turning into 0. So constant over 0, to summarize in a less technical way, a constant number divided by 0 is going to approach infinity. Positive or negative, depending on if it was like a negative constant or a negative on the negative side of 0. But constant over 0 is going to go off toward infinity. I'm being asked to find the limit as x approaches 2 from the right. Now remember, I can only do these infinities if I'm approaching it from one side. So it might help to look at the graph of this really quick so you can see what's happening. So let me just graph this function, because what I want you to remember is that it's a rational function. So I have 3x minus 1 divided by x minus 2. And I'm going to just use a standard window. And you can see that I have a vertical asymptote at 2. The reason why it's at 2 is if I plugged in 2 into this denominator, I would be dividing by 0. That's what creates vertical asymptotes. That's what creates limits approaching infinity. Notice that on the right side of 2, as I'm approaching 2 from the right, the y values are heading up without bound. And notice on the left side of 2, the values are going down to negative infinity without limit. So let's see what that would look like algebraically. Algebraically, what I would do is I would plug in numbers that are approaching 2 from the right. In fact, maybe I'll just try plugging in 2. So this is going to head off towards 3 times 2 minus 1 over 2 minus 2. So it's heading off towards 5 over 0. Now remember this extension. If I'm taking a limit as x approaches some number from the right, and the top function, this is like my f of x, and the bottom function is my g of x, the top function approached a number, c, which in this case was 5, but the bottom function approached 0, which it did in this case. That means I'm going off toward either positive infinity or negative infinity, depending on if the g was approaching 0 from the positives. And it was, because I'm approaching 2 from the right. So I'd be looking at values like 3, 2.5, 2.1. Those values are all larger than 2. So this would be a positive number down here. And this would be a positive number here. So this limit is going to head off toward positive infinity, because I was approaching 0 through the positives and I had a constant divided by 0. Same thing happens over here. It still heads off toward 5 over 0, but now I'm approaching 0 from the negative side. Approaching 2 from the left, that means x is going to be stuff like 1, 1.5, 1.9, and so on. If I plug these numbers in here and subtract 2, I'm going to get a negative down here. These numbers will still be positive, though, because 3 minus 1 is positive, 3 times 1.5 minus 1 is positive, and so on. So this is going to be a positive divided by a negative. It's going to head off toward negative infinity. The giveaway that it's either this or that is if I have a constant divided by 0. Constant divided by 0, it's either positive infinity or negative infinity, depending on if the bottom function was approaching 0 from the positive side or from the negative side. Okay, so let's go further here. Okay, so I'm looking at this function here. I'm approaching 3 from the left. I know there's going to be an issue there, because if I were to factor this, I have a vertical asymptote at 3. So I know I have an issue at 3. So what I need to do is figure out what is happening. So if I substituted 3 in here, notice I would have 9 and then eventually over 0. Constant over 0. So constant over 0 means it's going to either become positive infinity or negative infinity, depending on if I'm approaching 0 through the positives. Well, notice the numerator will always be positive. That's not an issue. But the denominator, I'm approaching 3 from the left. So this one would be positive, but this one would be negative. Because I'm approaching 3 from the left, meaning x is going to be 2, 2.5, 2.9. If I take 2 and subtract 3, I get a negative. If I take 2.5 and subtract 3, I get a negative, and so on. So I'd have a positive divided by a negative, so this is going to head off toward negative infinity. And I know it's going to be an infinity because it had a constant over 0. Okay, so then with this one here, I have the issue of a vertical asymptote because I have, if I plugged 5 in here, I'd have a 0. But now this time I have 0 over 0. So this means needs more work. Substitution really didn't do much for me in this situation, needs more work. So what we're going to do here is we're going to check out the graph. Okay, I'm going to go ahead and sketch the graph of this. So I have the square root of 25 minus x squared divided by x minus 5. And I'm looking to see what happens as I approach 5 from the left. So I'm coming this way. Well, clearly it's approaching negative infinity. And if you wanted to double check that, you could go to your table of values. Wow, I went way too far. Let's have my table set start at 0, and I'll just go in increments of 1. And I'll go back to my table. Okay, as I'm approaching 5 from the right, we can see that these numbers are getting larger and larger and more negative. In fact, let me have my table start at 4, and let's move in increments of 0.1 so we can really creep up to 5. So notice as I creep up to 5, my negatives are just getting larger and larger and larger without limit. So I can see graphically that as I approach 5 from the left, this limit was equal to negative infinity. Okay. Another option for example 7 would be to plug in values getting close to 5 and then just see what would end up happening. Okay, moving on. With this example here, I'm left with no choice other than to check values. I know that if I plugged in 2, let's see what would happen if I plugged in 2. I have greatest integer of 2 minus 2 all over 2 minus 2. So notice again I have 0 over 0 because the greatest integer evaluated at 2 is just simply, this just equals 2. So that means it needs more work. So let's just look at some values as I'm approaching 2 from the left. So I'm just going to make a table of values here. Remember, y is this whole thing. So let's say I were to plug in approaching 2 from the left like 1.5. So I'd have the greatest integer of 1.5 minus 1.5 divided by 2 minus 1.5. So that would be the greatest integer of 1.5, that's 1. Minus 1.5 all over 2 minus 1.5, which is just 0.5. And then this here would be 0.5. So I notice that when I plug in something close to 2, I get positive. 1 minus 1.5 would be negative 0.5, so I get negative 1. Because in the numerator, it was negative, but in the denominator, it was positive. Okay, let's try plugging in something closer to 2 on the left, just like 1.9. So then I'd have the greatest integer of 1.9 minus 1.9 divided by 2 minus 1.9. Well, the greatest integer of 1.9 rounds down to 1. And I end up with negative 0.9 divided by 0.1. So if you notice there, I end up with, this would just be negative 9. So it's getting larger. The negative value is getting larger. If I plugged in something even closer, I would end up with an even larger negative. Maybe we'll just try one more, 1.99. So I have greatest integer of 1.99 minus 1.99 all over 2 minus 1.99. Okay? And when you do the greatest integer, evaluated at 1.99, even though it's almost 2, it still rounds it down to 1. So I have 1 minus 1.99 all over 2 minus 1.99. So here I get negative 0.99, sorry for the squished room, divided by negative 0.01. Well, that would just end up equaling negative, oh, sorry, this is positive. Sorry. 2 minus 1.99 is positive. That would end up equaling negative 99. So what I'm noticing here is as the values of x approach 2 from the left, so they're less than 2, my y values are getting more and more and more negative. And I can see a pattern that it's going to be negative 999, negative 9,999, and so on. I can see a pattern. So this limit is negative infinity by using a table of values to investigate. Okay. So what have we noticed? I hope that you've noticed is that as the limit, as x approaches some constant, either from the right or left, if it equals positive or negative infinity, then that means x equals c is a vertical asymptote. And the same would be true if I was approaching c from the left. So maybe I'll just put that. If I'm approaching c from either the right or left, and my limit is equal to either positive or negative infinity, then that means there is a vertical asymptote when x equals c. Okay, so I have some of these I'd like you to try. So go ahead and try these, and then when you come back, we'll finish the rest of the video. See you there. To conclude our notes from 2.2, I just want to summarize and then apply. So for the summary, I want you to know that if you have a limit of x approaching either positive or negative infinity, and if it exists, implies that y equals a is a horizontal asymptote. So if x is approaching infinity and y is approaching a number, that's a horizontal asymptote. But if the other way around is happening, so if x is approaching some constant either from the right or the left, and the y values are approaching either positive or negative infinity, that implies that x equals c is a vertical asymptote. Let's define horizontal and vertical asymptotes of these functions. Starting with a, horizontal is when you ignore the smallers and just look at the higher ones. So it's the limit as x approaches infinity of just the 3x over x. X's would cancel, and I'd be left with a 3. So that's my horizontal asymptote for A. Vertical asymptote would be where the denominator is 0. So that, in this case, would be at x equals 2. So verticals are really easy to identify. Whoops, sorry, that was part A. And then part B, for the horizontal, I notice that the power in the denominator is larger. So if I were to just sort of look at the more dominant parts of numerator and denominator, I would end up with this. And then that goes to 0 as x goes to infinity. So my horizontal asymptote for B would be 0. And then the vertical asymptote, it's whatever value of x makes the denominator 0. So I notice that x squared minus 4 factors into x plus 2 and x minus 2. So if x is either negative 2 or positive 2, I'd get a 0 in the denominator, which is bad. So I have 2 vertical asymptotes. For C, for the horizontal asymptote, I notice the power is larger in the numerator, which means that if I were to reduce these or just look at the more dominant parts, it would reduce down to x squared. And as x gets really large, x squared is going to get even larger. And so it's not going to reach a limit. And so this has no horizontal asymptote. that's none. For the vertical part, there will be a vertical asymptote whenever your denominator is 0. Since x is the only thing in our denominator, then I cannot allow it to be 0. So the vertical asymptote would happen when x is 0. At a piecewise function, this is asking for what would the limit of f of x be as x is approaching negative infinity. So I would use this part because that's where x is less than 0. So remember, that's asking me for a horizontal asymptote. That's all that's asking for. So I ignore everything else, and I just look at the x over x, which cancels out and becomes 1. So the answer for part A is 1. And even though that's negative infinity, I'd have a negative divided by a negative, which would turn into a positive. For part B, it's asking for the limit of f of x as x is going off toward positive infinity. So that would use the one on the greater than 0 side. So I'm looking for this limit, which again is only asking for a horizontal asymptote. So these are both asking for horizontal asymptotes. So I just look at the higher power in the numerator divided by higher power in denominator. Notice the denominator is way larger. So I'm plugging in a gigantic number and squaring it, making it really big. 1 divided by a really big number would end up being a really small number and approaching 0. Okay, this one is asking for the limit as x approaches 0 from the right. Again, I want to use this one because this is on the right side of 0. So I find that limit as x approaches 0 from the right of 1 over x squared. And I know there's a vertical asymptote at 0 because that would make my denominator 0. So I'm going to go ahead and substitute. If I were to substitute, I'd get 1 over 0. So I have a constant divided by 0. I know that's going to either be positive or negative infinity. The question is this approaching 0 through the positives or negatives? And the answer would be positives because I'd be plugging in a number and squaring it. So these are going to be positive numbers that are getting really large. And so this is going to be positive infinity. And then approaching 0 from the left, I would use this side because that's on the left of 0. And that's not a problem at all because I can just simply substitute because I don't have any issues here. So I'll just plug in a 0 to the top and the bottom, and then I just end up with 2 for that limit because there was no asymptote there because my denominator was not 0. Okay, so for this one, we're going to use our calculator again to find the horizontal asymptotes of sine x over x. Now remember, that's the same thing as finding the limits as x goes to positive infinity and negative infinity of the same function. So I'm looking at the far right and far left extremes. So we'll take a look at this graph, and it looks to me like as x is going off to the right and left, that the y values are getting closer and closer to 0. Another way to verify that is to look at the table. Maybe I'll have it go by ones again, and I'll have it start at, maybe I'll have it start at 10. And I can see that these values, even though they're oscillating back and forth from positive to negative, as they oscillate, they're getting smaller and smaller and smaller, positives smaller and smaller and smaller negatives. So in fact, I can see that those y values are approaching 0 as x is going really far to the right and really far to the left. So you can think of this as another special limit. Two more special limits. The y values approach 0 on both the far right and the far left. Last but not least, there's a very special theorem here that can help us with some of the more complicated infinity limits. And basically, I can find a limit as x approaches infinity of a function by changing that to approach 0 and taking the reciprocal of the argument. Because you can sort of roughly think of, this is rough, this is not technical, but it's something you can think of it as. You can think of 1 over 0 as infinity, so to speak, because if you take a number like 1 and divide it by a really small number, you get a really large number. And if you divide a number like 1 by a really large number, you would get a really small number. So in a rough sense, you can think of 0 and infinity as like reciprocals of each other. So let's say that you have a really difficult limit as x is going to infinity. Well, you can change it to have x approaching 0 from the right, because you have to keep it positive, of the reciprocal of the inside. And then if you have a limit as x is approaching negative infinity of a function, then you could look at that same limit as x approaching 0 from the left of the reciprocal of the inside. So, for example, let's say we had this function and you were asked to find these limits. This is telling me to use a graph, but I kind of just want to show you what it looks like with just by hand. So let's say I wanted to find the limit as x is approaching positive infinity of x sine 1 over x. According to this theorem, which is proven, this is true, I can do this, I can change this into a limit as x approaches 0 from the right and just take the reciprocals of wherever there's an x. So wherever there's an x, I would just replace it with its reciprocal. So the reciprocal of x is 1 over x, and then conversely, the reciprocal of 1 over x is x. And so I'm hoping this looks familiar to you. It should. This would be the limit as x approaches 0 from the right of sine x over x. And we've learned this limit. Hopefully we've memorized it by now. We know that that limit is 1. And you could do the same thing and end up with the same conclusion for the limit as x approaches negative infinity. So it's a really, really great way if you end up stuck with something like that and we can't use our theorems because it's not a polynomial or anything. You can convert it to a 0 limit as long as you take the reciprocals of the x's. All right, so I will see you in class. If you have any questions, please come see me in tutorial.